Hi everybody. I will do the presentation about our group. Our group topic is incorporation of chorus and fine graded policy for high performance catching. I have two group mates. I'm Gary Jiasheng Xu, and my teammates is Tong Yi and Zhang Fengxiao. Okay, so the first part is problem definitions. So our definition of our group project and the problem is the chip multiprocessors, also known as CMP, is a widespread of today's high-performance application, and on-chip shared last level cache LLC plays an essential role in the power efficiency and reducing the off-chip bandwidth. So we actually want to build and invent a new algorithm to actually see can we furthermore improve the performance of the algorithm we have, and due to the hardware limitations, we want to invent an algorithm to further improve the performance. So the next part is the survey part. As you can see, there's a tables. The content of the table is the common cache access patterns. So we do a very simple service on that, so we can see that as one of the fine grid policy, SHIP learns that the behavior of the underlying replacement policy, which provide the opportunity to combine with chorus grid policy. The result shows that the reuse behavior is strongly correlated with the program counter, the PC, which inserts the line into the cache. The predictor is trained by learning whatever a signature has near or distance reference intervals. So furthermore, to reduce the hardware overhead, a few sets are sampled for the training SHCT. On an eviction of the line that is never used, the signature is trained negatively to indicate a distance reinforce. So by the contrast, the signature is trained positively on each cache hit. So since there are so many different policies deal with different access patterns and make use of various informations about access behaviors, we devote our effort to design a brand new algorithm which can incorporate the advantage of what we have just talked about. So the next part is experimental setup. So we set up this experiment have something unchanged and something changed. So the things that's never changed is we use the focal processor that built with the same settings. And what we changed is that we changed the 4 different mixed multiple program workload. So the workload is the variable that we are keep changing, and the focal processor built with same setting is the never changed part. Also, you can see here there's a table. So the experimental is simulated with 16-way cache set, and 1/8 of the total set are randomly selected as samples. So you can see in these tables, all those things are totally random. So that's also the experiment that we set up. So that's those things are the changing the variables. So I will further briefly introduce the results, also the analyze of those results. So actually we calculated the measurement of the speed up. We use these equations. The speed up is equal to IPC minus IPC LRU divided by IPC LRU. So what is LRU? LRU is the stack divided into 2 logical segments with the prohibition segment. So LRU is no, let me first introduce IPC. Sorry about that. IPC is introduction per cycle. This is what we use to measure the further how our algorithm is speed up due to the old algorithm. So IPC can indicate the measurement of SHIP or our algorithm, cumulative IPC also for the LRU policy. So our algorithm can be further measured by this equation. So let's see the graph here, the blue and the purple one. This graph shows that our algorithm have a better overall performance than SHIP with average 4.13% speed up compared to the 3.83% except for limb quantum. And for the graph right here, the red one, there's 4 mix. For the first 2 mix, our algorithm have overall better performance, but for the mix 3 and mix 4, you can see the last two one, our performance is not as we expected. It have a worse performance than SHIP. We think that the reason caused this situation to happen is that because the SHIP have a more adapted to traits such as limb quantum on single core. Also, a random sampling for SHCP makes the result less robust. So finally, come to our conclusions. We have 3 conclusions that we have made due to our experiment and our designed improved algorithm. So the first one is SEC, LRU, and BIP are combined to train the SHCP, which not only retain the advantage of LRU for resistance-friendly access, but also improve the SHIP to be trash-resistant and scan-resistant. The second conclusion is that SHIP is optimized for dynamic RRPV at insertion position according to historical access patterns. Catch hit and catch miss are treated equally to update the SHCP in a more reasonable way. So the last conclusion we have is that for the single core configurations, our algorithm have a much better performance than the SHIP, which our algorithm have a 4.13% speed up, but the SHIP only have a 3.83% speed up. And for the quadra core configurations, both our algorithm and SHIP have a similar speed up percent. Is around like 10% more than LRU. And that's our presentations. That's much everything about our presentation of our project. Thank you for your patience. Thank you.